What's up guys, today we're going to be talking about entropy and the second law of thermodynamics. So what is entropy? You can think of entropy as a way of quantifying disorder. For example, have a look at the arrangements of these balls. The one on the left is very ordered and so has low entropy, while the one on the right is very disordered and so has very high entropy. More rigorously, we define the entropy S in terms of omega, where omega is the number of microstates that make up the same macrostate. The second law of thermodynamics states that the entropy of a system can only increase over time. That is, systems of high entropy don't naturally evolve into systems of low entropy. In our previous ball example, we see that the second law states that this state on the right won't naturally evolve into this state on the left, but this state on the left could evolve into this state on the right. Okay, so let's look at an example. Here we have a beaker with some food colouring in it. As we can see, the dye is all nice together, everything's in order, the state has a very low entropy, but as we start to mix in the dye, then it starts to blend, everything becomes really disordered, and the state has much more entropy, as the second law of thermodynamics predicted. Okay, that's all for our video on entropy. Thank you for watching. As always, if you enjoyed the video, please be sure to like and subscribe and... Wait, what's going on? No, he can't do that. Wait, what? No, did someone play the video in reverse? What? Can I get a replay of that?
In this house, we obey the laws of thermodynamics!
So what's going on here? Did we just break thermodynamics? In order to understand that, we need to understand how fluids move. When you think mixing, you're probably thinking of turbulent flow. Turbulent flow is a sort of chaotic motion. You can see that the dye is moving randomly throughout the beaker, and you're probably thinking, there's no way you could separate the dye from the water. And you would be right. The entropy of the system has increased too much, and therefore you cannot reverse the process of adding the dye to the water. However, there is another way that fluids move. This brings us to laminar flow. Laminar flow is a lot less chaotic than turbulent flow, and occurs when high viscosity liquids are moving very slowly. This causes the fluid to flow in parallel layers without much disruption between the layers. In this example, we are trying to demonstrate laminar flow with a deck of cards. Each card represents a layer of the fluid, and the line on the top represents the dye in the fluid. As you can see, these cards are free to move and slide past each other, but they don't mix with each other laterally. Furthermore, we can see that no matter how much we move the cards, we are always able to unmix them without too much effort. We can also see this effect by getting a bird's eye view of the unmixing process. As we can see, the vertical layers aren't mixing. The streaks of dye are staying in layers like the deck of cards, and you can see the spots would form as we turn the mixer in the other direction because the layers are just coming back together. From this angle, it's clear to see that we were cheating a little. From the other angle, it looked like the dye was thoroughly mixed in the liquid. However, from this angle, we are less convinced that any mixing actually occurred. So what sort of liquid do we need to demonstrate an unmixing effect? Well, we can use the Reynolds number as a representative for whether the fluid flow will be laminar or turbulent. The lower the Reynolds number, the more likely we are to see laminar flow. The key factors in this equation are the speed phi, at which the liquid is moving, and the viscosity of the liquid nu. We should expect liquids of high viscosity moving at low speeds to have a low Reynolds number and therefore should exhibit laminar flow. In order to test this, I tried a few different liquids to see what was best at demonstrating an unmixing effect. In each test, I made sure to turn the unmixer slowly to hopefully get a close approximation of laminar flow. Here are some of the things I found. The water is not thick enough to restrict the dye, and it just flows freely and mixes in the liquid. As expected, because water has very low viscosity. The glycerol is what was originally used and is sort of our benchmark for good unmixing. My problem with the glycerol is that the dye would just float in it. So to get around this, you really need to mix the dye with some glycerol. The glycerol gave a very convincing unmixing due to its high viscosity. Next, I tried diluting the glycerol to about a ratio of 4:1 glycerol to water. This had a very noticeable effect on the viscosity of the glycerol, and hence we can see that it doesn't unmix as well. Also note that it looks slightly blue only because I reused the same glycerol. The honey is also very thick, with a higher viscosity than the glycerol. It unmixed well, but not noticeably better than the glycerol. So let's take a look at the machine causing the magic. It's essentially just a hollowed out plastic cylinder with a base and a handle on the top that I drew in SketchUp and 3D printed. The base was made to be almost the same size as the bottom of the beaker to try and make it fit snugly and prevent a lot of unwanted sliding and shaking. If the mixer like slid too much in the beaker, it would cause the dye to mix in the wrong directions, and then we wouldn't really get a very nice unmixing. However, I also couldn't make the base too big because it wouldn't fit in the beaker, and the beaker sort of has a weird shape at the bottom. It's kind of curved, so to like print a better unmixer, I would suggest making the bottom of it curved so that it tries to like fit snugly in the beaker. The problem with the plastic used to print the unmixer is that it's not very dense, so sometimes it would just float in the glycerol. To avoid this, I made the cylinder hollow and filled it with water before unmixing. This weighed it down really well and also stopped a lot of unwanted shakiness in the unmixing. The handle was made just by cutting a hexagonal hole in a rectangle and sort of just sliding it on. The hole had to be hexagonal so I could like actually turn it. So did we break the second law of thermodynamics? Yes! No. We claimed that we had increased the entropy because it looked mixed. However, this is not the case. The entropy actually didn't change that much, if at all. Furthermore, the second law only really applies to closed systems, so the system of the unmixer and mixing a fluid actually involves the person turning it. This person is constantly converting food into energy, and so their entropy is definitely increasing, and this needs to be accounted for too. So physics is not broken.